Hey everyone, and welcome. Today we're doing something a little different. We're not just going to talk about math. We're going to learn the language that nature itself uses to describe everything from the wind to the pull of gravity. And it all kicks off with one simple problem.
Right, just think about it for a second. If I asked you about the wind outside, you wouldn't just say 5. You'd say something like 5 miles per hour coming from the north. See? You need two pieces of information, a magnitude, how strong it is, and a direction. And that's where simple numbers just don't cut it. We need a richer language.
So, that first word in our new language, it's vector. At its core, a vector is just an arrow. Simple as that. It points in a specific direction, and its length tells you how strong it is. It's the perfect little tool for describing things like the speed of a car or the pull of gravity.
Now formally, on paper, a vector is really just a list of numbers. It's coordinates. But the real magic, the part you need to picture in your head, is that arrow. That arrow has a length, that's its magnitude, and it points somewhere, that's its direction. This simple idea is the foundation for, well, everything else we're about to talk about.
Okay, so we've got these vectors, these arrows, but what happens when you have a vector at every single point in space? Well, then you have what's called a vector field. Imagine the air in this room, with a tiny arrow at each point showing you which way the air is moving and how fast. Now here's the cool part. We can use calculus to get what I like to call a local weather report for any single point in that field.
So, for our weather report, let's start with a really simple question. If you're standing on a hillside, you can feel the slope, right? But how would you describe, with math, the exact direction of steepest uphill?
Well, the answer is this thing called the gradient. For any map where you just have a number at each point, think temperature or elevation. The gradient creates a new vector at that point that screams, this way is steepest uphill. So, on a temperature map, all the gradient vectors would point toward the hottest spot. It's basically our compass for finding the fastest change.
Okay, next question for our local report. Picture this. You're looking at one single point in, say, a flowing river. Is stuff flowing out of that point, like it's coming from a hidden spring? Or is it flowing in, like it's going down a drain? That question? It's answered by something called the divergence. It gives you a single number for any point that tells you if it's a source or a sink. If air is expanding because it's being heated, that spot has a positive divergence. It's a source. If water is swirling down a drain, that spot has a negative divergence. It's a sink. Simple as that. And for our final piece of the local puzzle, let's zoom in. I mean, really zoom in on one specific point. Is there any tiny microscopic rotation or circulation happening right there? This is exactly what the curl tells us. And honestly, the best way to get this is to picture that little pinwheel. Imagine dropping a tiny imaginary pinwheel into a fluid. The curl is a vector that tells you exactly how fast and on what axis that little pinwheel would start spinning. You know, even in a river that looks like it's flowing straight, if the water near one bank is moving faster than the other, there's a curl, and it'll make a leaf on the surface start to spin.
All right, so just to recap, we have our local weather report. Gradient, divergence, and curl, they tell us what's happening at one tiny spot. But what if we want the big picture, the total effect over a whole path or across an entire surface? Well, that's when we shift gears from derivatives to integrals.
Our first tool for seeing that big picture is the line integral. It sounds complicated, but all it really does is add up the effect of a vector field along any path you can draw. And its most famous job? Calculating work. The line integral of a force along a path tells you the total energy you spent, or maybe gained, moving something along it, like pushing a heavy box across the floor.
Our second big picture tool is the flux integral. So if a line integral is about flow along a path, flux is all about flow through a surface. The best way to think about it is putting a net in a river. The flux is just the total amount of water that's passing through that net every single second.
Okay, so we've got our local measurements like divergence and curl, and our global sums like line and flux integrals. And this, right here, is where it all comes together. This is the absolute heart of vector calculus. It's this beautiful, almost secret connection, linking what happens on the very edge of a region to everything that's happening on the inside. So here's the big question. Is it possible to know what's happening on the inside of a shape, all the sources, all the spin, just by taking measurements on its outer edge? It sounds impossible, right? But the answer, incredibly, is a resounding yes. The first version of this magic trick, is called Green's theorem. Just look at the slide. It's telling us that the total flow you measure just by walking around the edge, that's the line integral part, is exactly the same as adding up all the tiny little spins, the curl, across the entire area inside. The boundary literally tells you everything about the interior. It's wild.
And this is not just some abstract math puzzle. This idea literally powered the Industrial Revolution. No exaggeration. Because of Green's theorem, engineers figured out that the total work you get from one cycle of a steam engine is the exact area of that loop you see on the pressure-volume graph. An abstract idea became the blueprint for a machine that changed the world.
And what's just so cool is that this isn't just a 2D thing. Check out this table. Now, don't get bogged down in the symbols, just look at the pattern. Green's, Stokes's, and Gauss's theorems, think of them as siblings. They are all saying the exact same fundamental thing, just in different dimensions. What you measure on the boundary equals the sum of what's happening in the interior. The outside tells you about the inside. It is one of the most powerful and beautiful ideas in all of mathematics.
So why should you care about any of this? What's the big payoff? It's this mathematical language we've been learning. Vectors, divergence, curl, these big theorems. This is precisely the language we need to write down the fundamental laws of our universe.
I mean, just look at these equations. These aren't textbook examples. These are the laws of nature, written in the language we just learned. Gauss's law for gravity uses divergence to say, hey, where you find mass, you find a gravitational source. Ampere's law uses curl to say that an electric current creates a spin in the magnetic field around it. It's not a metaphor. This is the actual grammar of physics.
So, that leaves us with a final thought. We've just walked through a language that can describe a river's flow, the work of an engine, the pull of gravity, the force of magnetism. The question isn't what can it describe, the question is what's next? What laws of nature are still out there, just waiting for us to find the right words, the right vectors, and the right equations to finally bring them into the light? Thanks for joining me on this.